everyone. Here we are going to prove the one-step subgroup test. That is, here we are given a group G. Okay, G could be finite, it could be infinite, and we are given a non-empty subset H of G. H is non-empty and it is a subset of G. Okay. Now H satisfies a property that uh, give me any two elements in H. Okay. So given any A and B in H, we will have that A B inverse is also in H. Okay, this is the special property that H satisfies. Now we are going to prove that if a set of a group G satisfies this property, then this subset must also be a subgroup. Okay, so we know that by the definition of subgroup, uh, this subset of a group must be a group in itself under the same operation in the group G. Okay, so we are going to verify the various axioms. So first we have to show that one, uh, H is closed under the operation. Okay, that is, we have to show that given any x comma y in H, we need to show that xy is also in H. Okay, we have to show this. Then we have to show that actually, since the operation is coming from the group G, by definition it is associative, so we need not verify that. So next what we have to check is that the identity element in the group G is also present in the subset. Okay, and thirdly I have to show that take any element in H, its inverse must also be there in H. Okay, so here given any element in H, we know that that A is also in G. So we know that A inverse will exist in G, in the group G. Okay, now that A inverse may or may not be there in the subset. We have to if show that if H is a subgroup. To show that H is a subgroup, we must show that the A inverse, which is already present in G, must also be present in H. Okay, so we have to make use of two crucial things here. First one is non-emptiness. Okay, and second one is this property. Okay, so let's begin with that. So okay, now since H is non-empty, we are guaranteed that at least one element is there in H. Okay, now call it X. Okay, so let X be in H. Okay, now here we know that for any element A and B in H, we know that A B inverse will be in H, right? So let we will let the A be equal to X and B also as X, right? So here we know that X is in H, so A is in H and B is also in H. So by given property, A B inverse, which is actually equal to X into X inverse, is equal to identity element. It must be there in H by the given property, right? So the identity element in the group G is present in the subset H. Okay, so this axiom, the second condition for the group, this is satisfied. Okay, okay. Now again, we will let say A is equal to X. Okay, then or let A is equal to identity. Okay, and B is equal to X. We know that X is there in H. Okay, and we are letting A is equal to identity. We already proved earlier that identity element is there, so we can take A to be the identity element. Okay, and then the second element B, I am taking it to be X. Okay, Then by the given property, we know that A B inverse, which is actually equal to E into X inverse, which is actually equal to X inverse, must be there in H, correct? By given property. So what have we proved? Take any element that is given any X in H, right? X inverse is also present in H, right? So the third condition, so here instead of X I wrote A, so the same thing, right? So given any A in H, its inverse is also there in H, so the third condition is also satisfied. Now we have to prove the first one, right? So let say X comma Y be in H. Okay, we don't know what these X and Y are, but let there be elements X comma Y in H. We have to prove that XY is in H. Okay, if two elements X and Y are in H, we have to prove that XY, the product XY, is there in H. Okay, now we know that uh, since Y is in H, from earlier we know that Y inverse is also in H, right? So let A is equal to X and B is equal to Y inverse. Okay, then by given condition, what do we have? A B inverse, which is actually equal to X into Y inverse, the whole inverse, right? Which is actually equal to X into Y. This must be in H by given property, right? So, what do we have here? Given any X and Y in the subset H, we have that XY is also in H. Their product is also in H. So, the first condition is also satisfied. That is, it is closed under the operation, right? So the subset H satisfies all the three conditions of the subgroup. Hence, H is a subgroup of